Okay, so for part 2 of homework 1-2, we'll pick up with questions 7, 8, and 9. And question 7 at first looks fairly intimidating. It looks like it might have to be one where we do a system of equations. But if you actually look closely, you're not going to have to do that if you're careful about this here. So in particular, just kind of going through the measurements. So he's moving in a straight line. He accelerates initially for 1.5 seconds. Then during a negligible amount of time, he changes the magnitude of the acceleration to 1.1. With the new acceleration, he continues in the same direction for 1.2 seconds until he reaches a speed of 3.4. What was his acceleration during that initial period? So the reason I said that, even though it looks like there might be a system of equations because there are two phases, it's not going to end up being a system of equations because if we look at the information that we know for his second acceleration phase, we know 3 pieces of information, which means we can find any of the other missing information for this phase. So I'm actually going to start with the second because what do I know? Well, I know the acceleration is positive 1.1 meters per second squared. I'm just defining it as positive because that's the direction he was going. I know that he did this second acceleration for a period of 1.2 seconds and that he reached a final velocity of 3.4 meters per second. So if I look at this information, well, based on this I could find either his distance or, perhaps more importantly, I can find his initial velocity for the second phase of motion, right? I can find out what his initial velocity is. So if I use VOTAT, if I use that first of our kinematics equations, I just set this up. I'm looking for his initial velocity for the second period of motion. I know his final was 3.4. I know his acceleration was a positive 1.1 and he was doing so for 1.2 seconds. So then, solving for the initial velocity, I get his initial velocity was 2.08 meters per second. The reason that's very important, that tells me the final velocity from the first stage of motion. So the final velocity from the first stage of motion here then was 2.08 seconds, or meters per second. So I know the final velocity, I know his initial velocity because he started from rest, which they told me, and I know the time was 1.5 seconds. So at this point I now have 3 variables for this equation. So again, I don't have to work a system of equations because I can just do these two truly independent of one another. I just need to make sure I'm comfortable finding the final velocity and using that to help me find the acceleration here. So I meant to give you guys this answer to start off with so you could skip through. Sorry about that. But in any case, I get the acceleration to be about 1.39, about 1.4 if you're rounding it to significant figures, meters per second squared. So again, this one hopefully not too bad. You read through it, I know there's a lot of information, but if you break it up, if you identify all your pieces, not too bad to work through. This one I won't necessarily even write out the answer because it should be direct enough to get there. So the velocity of an object is given by this expression where t is in seconds. Determine the position of the object as a function of time. So we're looking for the position as a function if it's located at 1 meter at 0 seconds. Okay, so that last part we'll come back to in just a minute. So the key here is I've got the velocity function, right? It's 3.00 meters per second, and I know sometimes the units get kind of busy here. So sometimes it's easier to just drop the units, although for right now I'm going to leave them in. But anyway, so this is my original function. I want to find the position function as a function of time. Well, the way to do that is to go back from velocity to position. That's where we integrate. So I'm going to take this entire function over here and I'm going to integrate it. So my position function with respect to time, so I'm going to do vt dt, v of t dt. I just need to integrate each of these with respect to time, so that's where we increase the power of t and then divide by that new power. So originally this had a power of t to the 0, so now this would be 3.00 t to the first power, and I would divide that by 1, which obviously doesn't do anything to this. The next one over here I would increase this from 2 to 3 and then divide by 3. So 4.00, I'm going to go ahead and drop the units just so it doesn't get too busy. Divide by 3 and I get t to the third. The key here is I do have to include the c. Right, so this is my generic position function, but I want to try and find out specific information about the c. And that's where that last part comes into play. Right? They tell me the position is 1 meter at 0 seconds. Well, how is that helpful? That's helpful because That allows me to plug in 0 for t and then solve for c. So I know that the position of 0 seconds, so when I plug in 0 for t, both of those two quantities would go away, right? So I know the position at 0 seconds would just be whatever c is, and they just told me that this whole quantity, this position at 0 seconds, is 1. So the significance of that is they're telling us that c equals 1. So to write my actual equation, my actual function, again, I do need the specificity of c. My actual answer then is x of t, my position function in terms of t, would be, and I'm going to go ahead and write it in standard form, 4.00 thirds or 4 thirds t to the third plus 3.00 t to the first plus 1 for c. Okay, so it is very, very critical that you actually plug in the specific numerical value for c. If you left this in terms of c, you haven't actually answered the question for this situation. So hopefully an easy enough problem, but a very important one for us to make sure we're understanding. So I do hope you took the time to watch this and make sure you got that actual answer out of it. Alright then, so the last question on the second homework assignment, and we saw one very similar to this in class. So this is one I'm going to go ahead and write the correct answer, the displacement that he should have ran during that first period. How far does he run during the acceleration phase? It should have been about 6.86 meters. Okay, so if you got that answer and feel very confident with it, again, you can stop. Congratulations on finishing this homework out. If you did not, then continue to watch and I will help you set this up. So the key to this problem is setting up both phases of motion. So there's an acceleration phase and there's a phase where he's moving at a constant velocity, right? So setting up both pieces, both phases, and then identifying everything that we can for them. So the acceleration phase, I know that he started at rest. They gave me his acceleration here of 3.80 meters per second squared, which they told me is constant, and that's important that it's constant because I can use my kinematics equations. I don't know what the final velocity is, and I don't know what the time is, and I don't know what the distance that he traveled is, right? That's what we're actually looking for this question. But the key with the final velocity, and this is the key to the whole problem, even though I don't know what the final velocity is, because I can use my equations, I can relate the final velocity in terms of the acceleration and the time. So if I use VOTAT, right, if I use my first of the three equations there, I get my final velocity equal to 0 plus 3.80 t1 because that's how long he was accelerating for. Okay, so I'm going to keep that in mind right here. But at this point I do get stuck because if I look at my variables that I know, I have two unknowns, and that means I cannot solve for delta x like I would like to. Okay, so then I jump over here to the constant velocity phase. So let's do our constant velocity. Well, during the constant velocity, we know the only equation we're using is, right, delta x, my change in displacement over my change in time. Well, I just found the constant velocity in terms of t1, so this would be 3.80 t1. I don't know how far he went for the second stage, but I do know that however far he goes for that first stage, right, we're just going to take the total distance of 50 minus that. So I'm going to represent this in terms of x1 by saying it's 50 minus x1. So I've got my second displacement here in terms of the first one. I'm going to do the same thing with my time, right? I don't know how long it took for this phase, but I know that the total race took 7.88 seconds, and so the second period of time would be 7.88 minus whatever he did during the acceleration phase. So the reason that this is very helpful is at this point now I have one equation in terms of x1 and t1, and then I had the same variables over here, so if I jump back to my first measurements, let's set up another equation in terms of t1 and x1. Well, you could look through and do just about any of them you want. I think probably the easiest one, the one that I'm going to go ahead and do, is x1 equals, so I'm going to use my displacement formula, my displacement equation. So v0 t1 plus 1/2 at1 squared, and then I'm going to plug in the measurements I know. The initial velocity is 0. I don't know what that first displacement is. I don't know what my x1 is, but I do know my acceleration is 3.8. And I don't know what t1 is, but at this point I have the same two variables here that I have in this equation. So it is just a matter of solving a system of equations. The good news is we've already got this equation solved for delta x1, so I'm just going to take this whole thing and plug that in up here. Right, so I'm going to take that whole equation and just plug it in, and at this point, even though it gets tricky because it is a quadratic, the only thing we have to do is just get through the algebra. Right, just have to get through the algebra. So again, I'll go ahead and show this kind of coming all together here. We've got 3.80t1 equals 50 minus, I'm going to go ahead and do 1/2 of 3.8, so 1.9 t1 squared, all divided by 7.88 minus t1. I need to solve for t1, so I'm just going to multiply both sides by t1, right? Or excuse me, multiply both sides by the denominator, 7.8 minus t1. So when I do that, 7.88 times 3.80 gives me 29.944 t1, and then obviously I get a negative 3.80 t1 squared equals 50 minus 1.9 t1 squared. And because we do have both a t1 squared and a t1, that tells me that if I go back to my algebra skills, this is a quadratic, right? If I have both a squared and a singular and a power to the first power here, there's no way that I can solve this equation unless I use quadratic formula or factoring. So I need to get everything to the same side. I'm going to go ahead and add this over and subtract this over, right? So I'm going to add and subtract those over here. So I'll get 0 on the left hand side, and I'll go ahead and write this in standard form too. Adding the 3.8 over, I get a positive 1.90 t squared minus 29.944 t1, and then plus 50 because the 50 didn't go anywhere, so it was staying positive, like we got to do in this course, right? But anyway, at this point it's just a quadratic formula, right? You can do the quadratic formula, you can do that by hand, use your calculator, whatever you're comfortable with. If I do the quadratic formula, I get two possible answers, 1.898, and I get the second possible answer of 13.862. The problem here is the race was only 7.88 seconds long, so it definitely cannot be 13.8 seconds. That doesn't make any sense. So the only answer that makes any sense is 1.898. So if you want to round that off at 1.9, obviously you definitely can do so. Okay, so that's my time, and then using that time, we just need to find my displacement. So coming back to either one of these two equations, either this blue equation here or this green equation, we would then just take that value and plug it in. I would probably just use this blue one because it's already solved for delta x and therefore relatively nice and easy to plug into. So I plug this, I actually then end up getting 1.9 cubed because half of that times another 1.9, and that's where I got my distance of 6.86 meters. The good news I mentioned earlier in our last homework, you can double check yourself pretty easily with these questions, and what I mean by that is if you plug the time back into the green equation up here, hopefully when you solve for x1 you better get something very, very close to 6.86 meters. If you don't, then that tells me that we found the wrong time or we messed up our algebra somewhere along the way. Okay, so this question is a very good question because it is mathematically difficult. However, hopefully we get comfortable with the concepts of how we can use these system of equations and get very comfortable manipulating those together. Again, if this is the type of thing that gives you trouble, come find me so I can give you some extra support and some extra practice and help you figure these out.